Just look around you for a second. The phone in your hand, the car you might drive, the building you're in right now. None of them were made as a single piece. Nope, they're all collections of parts, held together by these powerful, often invisible forces. Today, we're going to explore that hidden language of how things are joined. I mean, really think about it. Bridges, airplanes, all our electronics, they're made of thousands of individual little parts. So what's the fundamental process that keeps our entire complex world from just, well, falling apart?
The answer, believe it or not, is one simple word: joining. It's this incredible art and science of connecting separate pieces to create something whole and functional. And the ways we do it are absolutely fascinating.
Okay, so let's start with the big picture. We're going to break down the fundamental ways that we get materials to, well, stick together. You see, pretty much every technique for joining things falls into one of three main families. You can either melt materials together with heat, you can physically clamp them together with fasteners, or you can bond them with some really powerful adhesives. We're going to start with the hottest one of the bunch, fusion. All right, let's dive into our first category, which is all about fusion. This is the family of joining methods that relies on some pretty intense heat to literally merge materials into one single piece.
The core idea here is actually pretty simple, but it's incredibly powerful. Fusion is all about turning a solid into a liquid and then right back into a solid. You take two separate pieces of metal, you heat them up until their edges just melt into one single pool, and then you let it cool. Once it solidifies, they're not two pieces anymore, they're one.
Now, within the fusion family, the key differences really come down to heat and whether the main material, the base metal, actually melts. You can see right here that with welding, the base metal itself melts. That's absolutely crucial for creating a single solid structure. But then you have brazing and soldering. With those, you're actually using a different metal that has a lower melting point, almost like a kind of hot glue to join the pieces without melting them. This is perfect for delicate electronics, or when really high heat would just warp the parts.
So, if what you need is the strongest possible bond you can get, welding is the undisputed champion. No question about it. By creating a single, continuous piece of metal where there used to be two, you're achieving the ultimate join.
Now, you've probably heard terms like TIG, MIG, and arc welding thrown around, right? Well, those are just different ways of creating and controlling the electric arc that melts the metal. For instance, TIG welding is known for being super precise and leaving a really clean finish, which makes it great for delicate work on things like aerospace parts. MIG welding, on the other hand, is much faster, so it's better suited for factory production lines and thicker materials.
And hey, it's also useful to know the lingo. The joint is just the area where the parts meet. The seam, which you'll often hear called the weld bead, is that visible line of new metal that's actually fusing the joint together.
Okay, so we've covered joining things with a whole lot of heat. But what if melting your materials just isn't an option? Maybe it would damage them, or maybe you need the joint to be reversible. Well, that's where force and chemistry come into play.
And that brings us to our next major category. Here, we're not relying on heat to fuse materials at all. Instead, we're using physical force or some pretty powerful chemical reactions.
First up, we've got mechanical fastening. This includes riveting, where you use a permanent metal pin. Think of the Eiffel Tower or the skin of an airplane, places where you need something that can handle a ton of vibration. Then, of course, there's bolting, which uses things like nuts and bolts. The huge advantage here is that bolted joints are incredibly strong, but they can also be disassembled for maintenance or repair. You just can't do that with a permanent weld or a rivet. And finally, there's adhesive bonding. And let's be clear, we are not talking about school glue here. These are industrial-strength chemical adhesives. In modern cars, for example, adhesives are used all the time to join different materials like aluminum and carbon fiber. It helps reduce weight and increase rigidity in ways that welding just can't. They spread the stress out evenly, creating a structure that's both lighter and stronger. So, we have all these amazing ways to join materials. But these are powerful processes that involve extreme heat and a lot of stress. What happens when something goes just a little wrong? This is such a critical part of the story. A bad join isn't just a cosmetic problem. It can be a catastrophic point of failure. So let's take a look at some of the common defects that professionals are always watching out for. First up is something called porosity. Imagine you're making a weld, and as the metal cools, tiny gas bubbles get trapped inside. From the outside, it might look perfectly fine, but internally, it's like a piece of metal Swiss cheese. It's full of tiny holes that dramatically weaken the seam. On something like a high-pressure pipeline, that could lead to a total disaster.
Even more dangerous, though, is a crack. This is an actual fracture in the metal. It might start out incredibly small, but under the stress of daily use, a tiny crack can grow and grow until the entire joint fails completely. This is one of the most serious defects you can possibly have.
And here's the irony. The very same process that creates a join can also introduce flaws. The intense heat from welding causes metal to expand, and then as it cools, it contracts. If that's not controlled perfectly, this cycle can cause the entire piece to warp and bend, a defect we call distortion, which can completely ruin the precise alignment of the parts.
This leads to a subtle but really crucial concept, the heat-affected zone, or HAZ. See, it's not just the melted seam you have to worry about. The area right next to the weld also gets baked by that intense heat. Now, it doesn't melt, but its internal structure can be altered, often making it brittle. This creates a hidden weak point right next to your really strong weld.
So with all these potential problems, how do we make sure that the millions of joints holding our world together are actually safe and strong? Well, there's a system for that. This is all managed through a continuous quality assurance loop. First, every joint gets inspected, both visually and with technology, to look for defects. Then it's tested for hidden problems using things like X-rays, ultrasound, or even physical stress tests. If any defect is found, it's repaired, and then the entire inspection and testing cycle starts all over again until that joint is certified as 100% perfect.
For centuries, we've mastered joining materials together with heat, force, and chemistry. But as we keep inventing new composites, smart materials, and advanced alloys, the challenge evolves. So the question we're left with is this: what incredible new methods of joining will we need to invent to build the world of tomorrow?